that represents the state of the world at some location. We can think of pixels as a common scenario where we have lots of variables laid out in a grid form, which definitely has lots of loops. So we've established that we can't use dynamic programming or regular belief propagation there. We touched on belief propagation very, very slightly. But we still want to know what is the state of the world overall for all our variables, even though we don't have one of those convenient situations. And it turns out that for certain problems, this is going to be possible, and we'll be actually guaranteed to get the optimal solution. So we said when we have directed graphs, these are phase networks or phase fields. Here we're going to have Markov networks. We're going to be working mostly with undirected graphs. You'll see that it's sort of fairly convenient. In fact, we're actually going to mix a little bit. So we're going to have a little bit of directed and undirected, but we'll see that in due course. And if you've heard of graph cuts, then you're a step ahead of the game because we're going to be sort of justifying why we use graph cuts in this context. So, typical problem that we might be faced with is there is the ideal answer. That is, this is what the image should look like. Someone has come along and randomly chosen a pixel here and there and flipped its bit. So now instead of being, let's say these are on and off, instead of being off, something is on, and vice versa. So you have this kind of corruption that's happened to your image. We call it noise. If you know that this is kind of the process that was used, that it was random, it wasn't sort of caused by something something specific, something spatially located. If it was random, then you would say, okay, I've got this kind of noise. I might try to model the noise and might try to denoise, to try to go from this kind of input to that, ideally to that kind of output. This is binary denoising because our world states, you can already sort of infer here, our world state is just two states of the variable. What is the pixel supposed to be doing, on or off? Has anyone used median filtering in images? Yeah, some of you have seen this in signal processing or image processing. So this might, to you, seem like a great candidate for using an image processing algorithm like median filter, which isn't wrong. I think it's a perfectly reasonable approach. It is very deterministic, median filter. Median filter just looks at a neighborhood around a pixel and says, okay, in my neighborhood, in the binary case, let's vote, right? How many votes for on, how many votes for off? We're going to do something that's much more flexible than median filter, and so we'll have sort of, maybe in simple cases we'll have similar results, but in more complicated cases we'll have far superior results because we can impose things like a prior. All right, so there's the multi-label version of this, which besides switching to a cartoon character, it's not just the point. Here, instead of the corruption being flipping of a bit on or off, instead now we randomly pick a pixel in the image, and now it gets some new grayscale value. So out of a discrete set of 0 to 255, say. So we've got this noise here, and maybe it's white noise, maybe it's sort of centered around a Gaussian, right? Maybe there's sort of a Gaussian distribution of noise pixels appear in this form. So it's multi-label because we might have different colors of noise, and also our character now has different shades of gray for their different elements. So it's not just that we have to decide whether a bit was flipped or not, we have to decide which of the categories of color a given pixel should have. So W, again, is discrete, either binary or categorical. Okay, so the problem itself is fairly easy to set up like this. You saw this coming already. You're going to have observed data where at each pixel I'm going to have some observed intensity value. Let's keep it simple, right? Intensity high or low for the binary case. And we want our world state to be this vector of what happens at each pixel. Only we're saying the pixels cannot be treated independently anymore, so we're going to enjoy the fact that last week we introduced conditional independence. So we're hoping that when denoising a pixel over here, it's not going to be dependent on what's happening over here, but it will be dependent on what's happening in its neighborhood. Of course, the neighborhood's dependent on its neighborhood and so on, but that's the premise. All right, so we expect in this kind of denoising scenario that most of the pixels will stay the same. We are also expecting that our output, our uncorrupted image that we're trying to seek, is fairly smooth. In other words, that the world state here for any two pixels that are neighbors of each other is actually the same world state or a very similar world state. Occasionally they will change, so for two neighbors will have different states. But when you look at how many pixels there are in the scene, there are far more whose neighbors are the same than ones whose neighbor is a different color. All right, so we're going to have probability distribution over our whole binary image. So we need to take into account all of the different localized W's. And so now we found ourselves talking about a Markov random field. Right? It's a field. We've got Markovian relationship between the pixels, or the W's for each pixel. And we're going to formalize this a little bit. So we're going to say, okay, we have a bunch of sites. A site is both the pixel and the state at that pixel, right? So we have n sites, big N. So that corresponds to different pixel locations. We have obviously n. We have n sites, and we have n random variables W, each one saying on or off. And then for each of those W's, we have a set of neighbors. And so this curly n is indicating neighbor, right? So just notice whenever there's curly or Greek, right, this is suggesting something slightly special, right? So we've got a set of sites, and we've got the neighborhood of one of the n sites. All right, so our Markov random field, to be a Markov random field, the following has to be true. We have to, when we look at the probability of the probability distribution over one of the random variables, so one of the pixels' true values, given the world states, and this subscript S\n. So this is saying the world, given the world state for all of the sites, the set of sites in the whole image, all of the sites except the nth one. In other words, I'm talking about a single pixel on that image, and I'm saying, okay, the probability of that single pixel, given all of the other W's in the whole image, equals probability of Wn conditioned on just Wn's neighbors. Now this means direct neighbors, immediate neighbors. Your neighbor to the north, the south, the east, the west. We can include diagonal neighbors if you like, but we can't include neighbors. This does not include neighbors that go, let's say, 2 pixels north or 2 pixels west, or 3 or 4. Is that clear? So we're calling these the first order neighbors. All right.
You're saying that's equivalent to the first.
I'm saying this situation must hold for us to proceed with what we're about to do. If you look at this probability, and someone says, oh, I've got a grid, or I've got a bunch of variables set up in a loop with loops in them. And we say, oh, interesting, okay, what's the conditional probability of a given node in that graph, given all of the other nodes in the graph? All of the other meaning \n, just a moment. And if we look at all of the others, and there is some relationship between distant variables and the one we're interested in, then the right side of the equation isn't true. And we can't proceed with it because it's not a Markovian relationship. It says, actually, we don't have this conditional independence situation where a given pixel only needs to know what its first order neighbors are doing in order to come up with its final estimate. It actually needs to know what its more distant neighbors are doing. It's not a Markovian relationship because the Markovian one is is always about this conditional independence. If you have the sort of neighborhood, that's your Markov blanket, and that's all you need. Yes?
It is like a topological generalization of the Markov chain model.
This is the probabilistic generalization of the Markov chain model. That's right. Topological, perhaps. I'm not very familiar with graph theory terminology
I mean, just like in terms of neighborhoods and stuff.
Yep, that's exactly it. So this is, we're saying, look at the neighborhood of the whole neighborhood of everything in the world, right, except n. And this is saying, well, just the first order neighborhood. If they're equivalent, we can proceed. We treat this as a Markov-Random field, non-directed model, right? And we can proceed with what we're doing. If it's not the case, that means you have higher, you have neighborhoods, larger cliques that need to be dealt with, that can't be dealt with in the pairwise way that we're doing it. All right. So, assuming that that holds true, we have a Markov random field. We know that we can express the overall probability. This is our prior on the world states, right? As this relationship where we're saying, okay, let's look at the individual potentials of cliques of variables. The cliques are just our little collections, our little sets. We like maximal cliques, ideally. This is potential, so we want this to be high. If this is high for a given clique, it gets multiplied by other high numbers, hopefully, and our overall probability of that configuration of W's is high. Z is our partition function. Sometimes, and you'll see an example in a moment, it's easy to compute, sometimes it's harder. Right. We have another way of expressing this. We said instead of the potential functions, we could use the cost functions, right? So our cost function psi, remember psi is just a negative log of phi, works the same way, except now instead of a product, we have a sum. So this is okay. We have this is a review from last week. So we're okay with this, right? We have this exponential of our negative cost. We still have the partition function, and we have this clique, right? That we're still worried about how big is that clique. All right. So let's look at a specific example. I've got a big image of just 4 pixels. With 4 pixels, if we write it in terms of potential functions, right? I'll have this normalizing term out in front, 1 over z, and then I'll say, okay, well, I've got an edge here, so I need, this is, if I pick these two, is that a clique or a maximal clique? It's a maximal clique. Because if you try adding a third variable to these two, like that one, you'll find that, well, wait a minute, they're not all fully connected. There's no connection between W1 and W3. So if I just take these two, that is, in fact, a maximal clique. There we go. I've got phi 1, 2 for the first one. And we end up taking all pairs. So we have 4 terms in total. And so we know what is the probability of this bold W, right? Because we're looking at W1, W2, W3, W, and 4. The joint probability of all 4 W's. It's going to be equal to this. Now, we've already done this with the chains and the trees. Sometimes we will be learning these potential functions. Sometimes we'll be handed them. Here, someone has just told us, whispered in our ears, and said, okay, the potential function, obviously you can have different potential functions. You can have phi 1, 2, which is its own potential function. It just talks about what happens on the left 2 pixels of this graph. And it could be very special and very different than phi 3, 4. Is that clear? We could have very different functions. But it just so happens, let's say to keep things simple, we've chosen that actually all the phi's are basically the same. They're just looking at the states of the variables and checking whether they're 0 and 1. And they're saying, well, if they're both 0, I'm going to have a high potential. If they're both 1, I'm going to have a high potential. And if one of them is 0 and the other one is 1, I'm going to have this comparatively low potential. Okay? Maybe we learned that. Maybe someone told us that. Let's not worry too much about it right now. The idea, though, is we celebrate and we say, oh yeah, that's good. That's a high probability solution if we find ourselves putting for instance, a 1 and a 1 into the same potential function, we get rewarded for that. We put a 0 and a 1 somewhere, that's less likely.
Why can't we have the same relationship between W2 and W4, like a diagonal?
We could create an edge between W2 and W4. We're allowed to do that. It would be a different graph than this is. So you would then be modifying this equation, and that's fine. Yeah. Okay. And then the maximal cliques would be different. If we did W2 to W, if we added an edge here.
And an edge the other way, W1 and W3.
Let's keep it simple. What happens if I just add an edge here? Well, you can keep adding edges as much as you like. Well, at that point, I think you're done in this 4-pixel example. But let's say I just add an edge here. How many maximal cliques are there? 2. Okay. So hopefully that's clear. If it's not, maybe we can work on it or talk about it after class. Yes.
Why aren't there 4 maximal cliques? If you took like,
I'm sorry?
say W2 and W3 is its own maximal clique.
Well, I didn't quite understand the question. W2 and W3 are maximal clique, yes?
Didn't you just say there was 2 maximal cliques?
If we had created an edge, sorry, I'm not painting on it.
Oh, okay. If you had an edge between
W2 and W4,
yeah.
how many maximal cliques are there?
2.
That's it. It's great having a whiteboard in here. All right. So let's just pick apart this situation. These are our potential functions. We have 4 variables making up the world state. So the joint state of W1 through W4 could be represented as just a binary number, 0, 0, 0, 0, 0, 0, 0, 1, right? Meaning all the pixels are off, 3 of the pixels are off, 1 of them is on, right? And so we could just enumerate all 16 possibilities of what can W1 through W4 be doing. So that's those are the odd columns, right? For each of these configurations, we can then plug that in here and say, all right, fine, phi12 with 0, 0, that gets a 1. Phi23 with 0, 0, that gets a 1. And we plug it in and do the computation, and we end up with 0.47176. Why isn't this 1.0?
Because you have this normalizing constant.
Because we have this normalizing constant, z. Exactly. So if we might go through and do an unnormalized version of this, where we would say, okay, well, the unnormalized probability of this configuration is 1, and the unnormalized probability of this configuration is some other number, probably 1 times 1 times 1 times 0.1, right? Because of this, and we have these unnormalized numbers, and then we sum up what's happening in each of these columns, and that's our z. We have to say, what is the probability? Remember, probability of this happening has to be, what's the probability of this happening in the face of all the possible things that could have happened. So overall, you should see that the joint probability is highest here for configuration of all pixels off. And the other place where it's equally high is here, all pixels on. Highest probability configurations. Everything else, something in between. Right? What are ones that score particularly badly? Ones where they're mixed, right? On, off, on, off. Well, so you're very much anti-smooth here, if that happens. All right, because we just had 4 terms, we're able to compute all of this exhaustively, and we're able to compute z. Typically, you might have too many variables. If you have 10,000 pixels, which is very easy to do, right? You don't have to have a big image for that. 10,000 pixels, and you've got 2 to the 10,000th power, right, terms that you have to add up. So computing z becomes kind of intractable. But we take heart in the fact that maybe what we're interested in is comparing 2 suggested configurations of the world state W. We just want to say, is this configuration higher probability than that configuration. And since the z in the denominator is always the same, we can compare relative probabilities, even though they're not strictly probabilities until we do that normalizing. All right. So if we take samples from a larger grid, that was a 2 by 2, it was 4 pixels, right? That was a 4 pixel grid. If we take some 320 by 240 grid of pixels, and we say, okay, well, what does that look like? This prior that we've imposed, this smoothness prior with these weights here, what does that suggest our images ought to look like? Well, it's hard to compute sort of the it's hard to compute the average version of that, but we can certainly guess first off what's going to be the highest scoring configuration. Anyone want to guess?
Completely smooth?
Completely smooth. Completely smooth black or completely smooth white. Either way is fine. Right? That's the highest potential, highest probability configuration. But what we can do is we can take samples from our probability distribution over 320, 240 pixels. And one thing that we haven't really talked about is how to do that. If you have a bunch of variables like this in a big grid, and you say, well, what's a sample? What's an example of a configuration of W's taken from this situation that respects as much as possible these potentials that I've defined? Then one way to do it is to do Markov chain Monte Carlo. Now we're not going to go into great detail about it. Those of you studying machine learning will probably maybe have already seen it. But one version of Markov chain Monte Carlo is to do Gibbs sampling. So we've got Gibbs distribution, so we can do Gibbs sampling here, and essentially that amounts to treating, let's use this image, treating our layout of all of our variables, right, all the pixels in a grid here, as a very high dimensional world space, right? And saying, okay, I'm going to pick a pixel, and I'm going to fix its state. I'm going to say you are in the on state. If you are in the on state, let me go to all of the pixels that depend on you and see what they say. And so Gibbs sampling is searching through this very high dimensional space by locking down one variable and then sampling from the whole probability distribution of over all the variables and saying, okay, what configuration would you be in if we locked that to state 1? Now, because we've defined this preference for smoothness, right, then most of the neighbors of that will say, oh, I'd like to be in state 1. But we have to keep going. We have to say, all right, we'll keep going further and further out, further and further neighbors. And remember, we have this non-zero probability of changing the sign between two neighbors, right? So maybe not immediately, but eventually we would hit a point where, because we're sampling, right, it's stochastic sampling, we might flip the sign. And as soon as you flip the sign, well, the neighbors of that will then prefer to be in state 0, and they'll keep going in that sort of way. So that would be just one little step in Gibbs sampling. That would be saying, or Markov, that's a specific example of a Markov chain Monte Carlo sampling, where we've just picked a single point, fixed it, and then seen what else happens with all the variables. Now, normally what happens is you do that, you see what happens, and then you unlock that variable, and given your current setting of your variables, you fix something else and do another pass going back. In other words, we'll then say, okay, well, I'll lock you to be the same as you are. Now, everybody gets to resample based on your current setting. And so we kind of do these multiple passes, and it's very inefficient to do in a very high dimensional space. But here, our dimensional space is usually quite localized, right? So we only have to look at small sets of neighbors. So it's actually not terrible. And what we're seeing here is 4 distinct images where we've done Gibbs sampling for a while. You run it for a while. Gibbs sampling for a while to see basically what is this smoothness prior doing to our world state. And it says, I like images like this. They're not identical to each other, but they are all, you should see, fairly smooth with sort of continuous boundaries, no individual pixels floating like we have when we have introduced noise. Okay, so that's sort of quick tangent on MCMC and Gibbs sampling. Might be useful to you in your other endeavors. All right. So back to our denoising goal. We want to figure out what is the uncorrupted image at inference time. So we're skipping over the whole training again, just like we did last week, and saying, all right, I want to figure out this posterior probability of what state should each of the pixels be in, given some observations of intensity. Now, if we were doing discriminative, if we were doing this as a discriminative model, we would just have a distribution over world state that would take a function of x. But we're not doing that, right? We're going to use all of Bayes' rule. We're going to talk about probability of x given w, which means that we're using a generative model, right? We're going to talk about this probability of x given w. We're going to talk about its prior. We may or may not talk about this partition function. But we're going to do this so that, because this probability of x given w is where we're going to be able to model our noise. And this, right here, this prior probability over what w's we expect to see, well, this is our way of imposing the smoothness prior. All right, so we've got our generative model set up. We just have to define what we're going to use. So the probability of xn given wn, well, so the probability of xn given that the world is in state 0 is some Bernoulli distribution, right? So we've got 2 categories to choose from on some parameter rho, and probability of xn given wn that the world state that the pixel is on is just the complement, Bernoulli distribution on 1 minus rho. So probability of flipping the polarity of our given pixel. So if rho is really just random, right, then that's going to be 0.5, and it means that pixels get randomly flipped, but maybe rho is some other number. So it might be useful to learn that, to learn how your noise is working in this particular process. We're going to say, okay, well, we're not too worried about that right now. We're going to press on towards inference. But remember, that was just this likelihood function, conditional probability of xn given wn. We also have our prior, the Markov random field smoothness assumption. Now, the cool thing is that we're going to be able to do maximum a posteriori inference using graph cuts. We did map inference last week using dynamic programming, right? Particularly the Viterbi algorithm. This week we're going to use graph cuts. But let me explain again how this fits in terms of our graphical model. We still have our observations. This is saying, oh, I saw some intensity at site 3. There's a random variable representing the world state at site 3, and there is a directed edge between them. Saying, okay, well, if the state is on, then this ought to be probably on, subject to some bit flip. There's also a set of undirected edges connecting each world state to its first order neighbors. So what we have here is a mixed graph with undirected and directed edges. And that's not so uncommon, but here we find it convenient, right, because we have this Bernoulli process for the noise, and we have this Markov random field prior on what we expect from our world states. Okay? So, when we want to find the maximum a posteriori world states, this is the answer we seek. What is the configuration of each of the pixels? We know that, right, after Bayes' rule, we're going to have probability of w of the joint of all the w's given all the x's. So, to maximize that probability, we have figured out that we can just look at the numerator in Bayes' rule and say, okay, well, just choose the w's that will maximize this product of probabilities. You take the log of this, the products turn into sums, so we now have the sum of, we have product of a times b, now we have the sum of a, sum of the log of a plus sum of plus log of b. We can take these probabilities, right, and convert them using the log into size. So now we're talking about, well, basically down here we're talking about costs. Here we did just the prior, turning that into a cost, right? And here we've wrapped that up into pairwise terms, and we've wrapped this up into unary costs. The unary cost, as always, is saying, all right, at site wn, tell me what is the cost of associating that w with that x. And the pairwise terms are saying, all right, I've got some kind of prior. I'm going to enforce that prior. I want site m and site n to maybe be in agreement or as much as possible. This is great, right? This means that now we can go through our graph of sites and try to find a solution that just maximizes these terms at the same time. We can't just maximize one without the other. We have to maximize both simultaneously. Because we can pose our problem this way as being unary costs and pairwise costs with just pairs of nodes, right? So this is very important. We have to have the Markov assumption so we can talk about pairs. This means that now we can talk about 3 different cases, which are all variations on the theme. The binary MRF case that we've been talking about with the bit flip, the multi-label MRF, where maybe you have a cartoon character with 6 shades of gray, right? And in both of these, as long as the cost is submodular, then we can do exact map inference. So you should be getting excited that we can find the exact solution, no approximations, no cut corners. There's a third case, the multi-label MRF, where the costs maybe are more general. They're not submodular. We'll talk about that later on Thursday. But the idea is that we will still be able to use graph cuts, but we won't be as convinced that we've arrived at the optimal solution as we are in the first 2 cases. Right. So keep in mind, we're going to use graph cuts to solve our Markov random field problem. Now, we're going to take a slight detour and say, all right, remember we want to use graph cuts. We think graph cuts will be good. What are graph cuts? And well, to answer that, we kind of need to look at the maximum flow or minimum cut problem. The max flow or min cut problem is beautifully defined in many computer science algorithms textbooks. And we're going to go through it here and work through an example so that it's very familiar. So keep in mind, we still want to come back to probabilities, random variables, but we're going to do this very kind of deterministic thing, which is a pretty standard thing in computer science texts. The max flow problem, first we'll do it as max flow, then we'll see that this is actually the same as min cut. Max flow problem. I have a bunch of nodes. All right, so yes, these nodes do correspond to pixels eventually, but don't worry about the pixels right now. I have a bunch of nodes. I have 6 of them, in fact. I'm going to create 2 virtual nodes, a source node and a sink node. And if someone connects these nodes to each other with some configuration of pipes, then you can imagine, you can visualize this as water flowing through these pipes. But some pipes have more capacity than others. So we're going to write in here on each edge the capacity of this pipe to carry water. So you've got this network. Someone is pumping an infinite amount of water into the source, and not an infinite amount of water is coming out of the sink, because the water, as it goes through these pipes of various diameters, is filling up the pipes, saturating them. They can't get any more full. They're pumping as much water as they can, which means that the water is arriving at the sink at only kind of some trickle compared to the infinite flow coming in at the source. All right.
But
we-
surely that has to come into that.
The flow into the sink.
Eventually, yeah, once it gets a steady state.
So once it reaches a steady state, you will have maybe an infinite total amount of water because we're just flowing water, but the rate of water coming through the sink will be limited. So imagine I've got the Niagara Falls is pumping seemingly infinite amount of water through my little toy pipe set that I've constructed using these edges. At some point, no more water will only be going in at a certain rate, and any more water that's coming down onto that spot is just going to go around because it just can't go through here. This pipe network will be full.
Your model doesn't support, as far as I know, another exit.
That's right. So the infinite flow here is wasted. Basically, we're saying it can't go.
It can only come in as fast as it can go out.
That's right. That's exactly it. So we've got our graph, we've got our capacities, and we're saying, oh right, and the capacities are non-negative. All right. So I think I've just described this. Right. When we are pumping water in, where there's as much water as this system will possibly take, if you have an edge that's saturated, in other words, its capacity is already being met, then you have created a path that goes from the source to the sink. If the capacity isn't maximized, so there's still spare capacity going, then you could push more flow, and that's not a saturated edge yet. Okay, so we'll see an example of this now. So the Augmenting Paths version of how to compute max flow. We have a source. We have a sink. We have a bunch of nodes. The capacities on each edge, we're going to write them in. They're currently grayed like this. The first number here is 0, means how much capacity are we using right now? Right now, none. We haven't started the process at all. Slash, how much capacity is there total in this pipe? So this one has a capacity of 7.4. This one has a capacity of 4.1. So that's a little bit smaller. This one has a capacity of 0.9. So really quite a small pipe here. And so someone has figured out what the capacities are for all of these pipes, listed them on here. Before we start the augmenting paths, none of them is being used at all. There's no capacity, no water really flowing. So we start off, we pick a path, we pick one at random if we like, and we say, okay, let's see how much water we can pump through this path. From source, it has to come in, goes out through the sink. What happens? Well, we pump in as much water as we can here. This says, I'm happy with 7.4. This says, I'm happy with 7.1. So if this one's only if this one only has capacity for 7.1, then already that means there's going to be 7.4 minus 7.1, 0.3 of this capacity not spent, right? And then, oh, this one only has capacity 4.1. So for the path from the source to the sink that goes this way, all the water, the only water we can pump through is 4.1. So we'll saturate this one, so we'll turn it red. 4.1 out of 4.1, completely saturated. That means we've used up 4.1 of this guy's capacity and 4.1 of this one's capacity. There is still spare capacity here, and there's still obviously spare capacity here. We've only saturated one of our links, but we have saturated it, and therefore for this particular combination, this path, we can't do any more. We can still use this to go other places. There's an arrow going up here and maybe out here. So there are still some options to try to take advantage, to leverage that spare capacity. So we pick another path now, and we go, all right, here, here, and then let's go around this blockage, right? So we'll go up and around. But this one only had a capacity of 1.3. So we saturate that, we use all 1.3, we take away 1.3 from the total capacity of this, we take away 1.3 from what was left here and from what was left here. So less of our flow, or more of our capacity is being consumed, right? We still have some spare in these two edges, but these two have now been saturated. Is everyone okay with what I'm doing? Can you get the idea of the capacity and the used capacity? Yes.
So you're using that edge from 6 to T as well in this case?
Yeah, at the moment we're modeling the problem, so we're sort of building up to this I'm using infinite water situation. We're building up and we're saying, okay, well if I turn on this much, where does the water go? So if I turn on 5.4 amount of water, 5.4 will go here, 5.4 will go here, and of the 5.4, some of it will go this way, some of it will go this way. So we're using total 5.4. Now we can keep track of everything that's leaving this node to sort of keep track of that. The goal is we just want to maximize that. All right. So we pick another random path from source to sink. Okay, this one goes up and over. So, right, this one's only got a capacity of 1.5. So it saturates. We take away 1.5 here, use up 1.5 here. Keep going, you get the idea. Right, pick another path. This one is the limiting factor here. So in any path, you're always sort of limited by the minimum capacity that's remaining. This one only has 2.9, so everybody loses 2.9. Remember, this one was already being used a little bit, so now 2.9 added on to, what was it, 1.3 previously. And we now have 1, 2, 3, 4 saturated edges. Are we done? Can we pump any more water through this system? So I see a head nodding yes. Yes, we can pump some more water through the system. Where is there some spare capacity?
You could go from 1 to 2, and then from 2 to 4, and then from 4 to, yeah.
So we've got, so I think the suggestion is 1 to 2 and 2
up to 4.
Up to 4. Okay, so that's not my next slide, but I think it's absolutely right that we could do that. If we went from source to 1, what would we have then if we went that path? That's got plenty. That's got 1 to
You could add
4.
at least 5.2.
That's 7.1.
Oh, sorry. Yeah. Just
You
0.9.
you got 0.9, but we could add 0.9, and thereby saturate this edge. But that's right. That's absolutely right. Yes.
Do these nodes conserve flow?
What does it mean to conserve flow?
I don't know, like in Kirchhoff's law, some of ingoing is some of outgoing.
Yes. So they do
I mean,
conserve.
besides the source and the sink, of course.
They do. Yes, they are just normal conduits for the flow. Currently, there's nothing else attached to the nodes in any way. Even though we were talking about unitary costs for now.
Just looking at 3, and I don't know. I mean, if you add up the ingoing and the outgoing capacities, you don't add up to 0.
The capacities,
Yeah.
right?
Also,
So that's me attaching some big pipes and some little pipes.
yeah, I mean, actual flow has to conserve,
Yeah.
not capacity.
Yep, that's it. You got the idea. So my next slide is a different one, but saturates the same 0.9 edge, right? Going from here to here. Still 0.9 is the limiting factor if you do that. Yeah, I think we're done. At this point, if we try to find another path that goes from source to sink, there's no spare capacity left, right? Not a continuum of spare capacity. Sorry, how are we doing for time? All right, we'll hurry up. So, what does this mean? We have these saturated edges. The Augmenting Paths algorithm has found a way to separate. Yes, I know, we've been talking about connecting the water from there to come out here. But if we look at where the water has saturated the capacities, you could think of these as this separation of water that is on the source side and water that is on the sink side. It will have to pass through one of these edges, these are all maximally saturated. But we could think of cutting these saturated edges, and that is going to be the solution to our augmenting paths algorithm. This is saying this is the optimal separation between nodes that are attached to the source and nodes that are attached to the sink. Right, so it's a bit of a leap, right? Because we're not using the water analogy. It sort of served its purpose, but we have to kind of leave it behind now. We're saying if you wanted 5 is attached to the sink. If you wanted to attach 5 to the source, that means you would have to make this cut go around 5 somehow, like that. And if you made it go around, you would be using your capacities inefficiently. This is the most efficient use of the capacities we had in our graph, and as a result of which 4 and 5 are attached to the sink, and the others are attached to the source, and that's it. So was there a question?
These pipes are the ones that are most likely to burst.
These are the ones, yes, that's right. Exactly. That's a great way of looking at it. Yes?
So why how do you know which arrow is included? Because, for example, like you cut 2 arrows with each. Mm-hmm. So from 5 to 3.
Fair enough. So we had this configuration of an arrow going this way and an arrow going this way.
Mm-hmm.
But we only saturated this one.
Oh, okay.
We never, for instance, found it useful, which you will have configurations like this where it's possible to end up at 4, and the best path might be to go 4, 5, cross here, down, and get to the sink, right? So it's possible that we might have used some of this capacity, but we will find that you don't actually end up using it. It would be a very unusual, if not impossible, configuration that you would end up saturating both directions. So this is the augmenting paths algorithm. Typically, you wouldn't actually choose the paths completely randomly. You would actually sample the paths and choose one that has the greatest capacity, right? You sort of say, okay, well, I'm going to see what saturates next, but I'm going to start with sort of the ones that are going to give me the most flow, and that keeps you from ending. That sort of gives you a more deterministic solution, well, a deterministic solution, whereas this can get you into some sort of backflow problems if you just make randomly. So we've got our cut. And by the way, the cut, yes, this is where the pipes are most likely to burst. The saturation values, the capacities of, sorry, not capacities, the used flow that we have at each of these locations, you can sum that up, and that'll be representative of the cost of this cut. So that's sort of a hint going forward. So back to graph cuts and our binary MRF problem. World can be 0 or 1. We said we've got unary cost, we've got pairwise cost. We're going to set up our sort of 0 diagonal pairwise costs. We said, right, the probability of 2 pixels being labeled 0. Sorry, this is, these are costs, not probabilities. So this is our pairwise cost for 0, 0 is 0, no cost for putting 2 things that are identical next to each other, and there's some theta, some non-zero cost for having 2 opposite world states next to each other. We set up our binary MRF problem, Markov random field problem, as a graph with a source and a sink, and all of the pixels in between. So here we have a nice small image with 3 pixels by 3 pixels. Each one is going to be on or off. And we're going to be pumping flow into the source, trying to get it to the sink. And we're going to try to see which pipes are in danger of bursting. And when we do that, we will, just like the augmenting paths algorithm, we'll figure out that there's some optimal cut through the edges of this graph, including the edges to the source and the sink, mind you, right? So notice we were cutting a sink connection here as well. All right, so we will we will have this graph, we will calculate the cut, and when we calculate the cut, we will find that each of the pixels in the image is attached either to the source or to the sink, not both. Pixel will be one or the other. And being attached to one will mean 0, and being attached to the other means W equals 1. All right. This is, I think, a convenient place to stop. So we'll resume with graph construction on Thursday. All right, thank you.